Our first chapter, entitled Axis of Rotation and Angular Properties, is quite a long one. There's a bunch of definitions we have to go through, along with concepts and a great deal of problem solving. So let's get into it. First of all, what is rotational motion? Okay, up till now, we've treated everything as if it were either a point or a shape. But even when we had shapes, we would just deal with it like all of its mass was concentrated at one point, its center of mass. And then we'd pretend it acted like a point at its center of mass. So we're going to continue with our thread of starting simple. This is basically what we do in physics at this level, and actually at every level. You start simple, and then we keep layering on more reality until eventually you get to a much better description of the universe. So we're going to address the fact that things rotate, and many interesting applications arise from this. Let's start. What are some types of rotating objects and how are they important to society? The list is endless. Hopefully you expected that, and hopefully you came up with some different examples that are being shown here. But here's some. Turbine generators. Turbine generators, they change mechanical energy, like the flow of water or nuclear energy, and they change that into electrical energy, and they supply electricity to businesses and homes. Helicopter blades rotate. They lift the helicopter into the air. Electric motors that can power electric cars, they power circular saws, they power vacuum cleaners. Something as simple as a swivel chair. If you're sitting in a chair and you spin, that's rotational motion. Curveballs. Baseball pitchers throw curves. They move, they rotate. Automobile and truck tires. They propel cars and trucks down the road. So what's a common feature of these examples? All of those objects are rotating about a line somewhere within the object, and we call that the axis of rotation. You could also have an axis of rotation to the side of it, but then you've got a different problem. We're not going to worry about that for now. So here we have a globe, a sphere rotating. And see the little red line there? Red line starts there, goes through the object, and comes out the bottom, and you can see how it's spinning around. We're also going to assume that all of these objects are rigid bodies. That is, they keep their shape and are not deformed in any way by their motion, which again is not true, because as the Earth rotates, it is slightly deformed. It is not a spheroid. It is a prolate spheroid. It's slightly flattened at the two poles. Again, not going to worry about that now. Does the axis of rotation have to be a part of the rigid body? With the one example that I talked about earlier, the exception where you could have an axis out here and this whole object could be spinning around it. Does it actually have to go through the physical body here? Think about that for a second. Nope. Just take the example of a chocolate-covered donut here. If we were to rotate or spin the donut this way, its axis of rotation is right here, and using our vector notation, this is coming out of the page, and of course it's going right through in. So you've got a pole coming out, so the axis of rotation is in the empty space within the donut. We're going to define another new unit that will help us explain this rotational motion. First of all, let's start with the circle. Why does a circle have 360 degrees? That seems like an odd number. So a little research on Wikipedia and the web, and there's a couple of proposed ideas for that. Some folks believe it stems from the ancient Babylonians, and they had a number system based on 60 instead of our base 10 system. Not sure why. That would be something that would be pretty cool to look up. Others track it back to the Persian or biblical Hebrew calendars, where they had 12 months. Each month had 30 days, so there's another 360. Notice none of these have anything to do with the actual geometry of a circle. So mathematically, we're going to come up with a new way of doing this that makes more sense, that'll work better with physics, and we're going to define the radian. We have a circle here, and we're going to say the axis of rotation is right here pointing out of the board, so the circle is rotating this way around its axis of rotation. Start with a piece of the circle at point A. I have a little point right here on the circumference of the circle, and we're going to rotate it counterclockwise. So point A, whoever was here, let's say it's a bug or something, is now at point B. You can see some letters here. We have theta, that's an angle, that's pretty easy. R is the radius of the circle. This S is something new, and we're just going to leave him there now and talk about him shortly. If there were a bug here at point A, as the circle rotated, the bug moves over to point B. We say that the bug swept out an angle theta. Right? There's theta right there. We can also say that the angle theta subtends an arc length of S. So there's our definition of what S is. We're going to call S an arc length. Note that the points A and B are always at the same distance r, right? The radius from the center of the circle, also the axis of rotation. That, of course, is what it means to be a circle. When you're on the circumference, you are always the same distance from the middle. We will now define the angle of rotation theta. Again, the circle rotated and somebody moved from point A to B. The circle rotated an angle theta. And we're going to define that as the ratio of the arc length, which is S, to the radius. Can you see how this is a much more natural definition of the angle of rotation than basing it on some old calendar or arbitrary numbering system? We are relating a piece of the circumference of the circle to the angle that it subtends when it rotates. So we will have theta is equal to S over R. Theta is the angular displacement. And let's pull this down. We are now defining rotational angles in geometric terms. It's the ratio of the arc length covered by an angle and also the radius, all three very natural quantities of a circle. Angular displacement is now unitless, since it is a ratio of two distances. For example, S could be measured in meters and R in meters. Meters by meters, you don't have a unit. However, we're going to call it something. We're going to say that this angular displacement, this theta here, is measured in radians. Not degrees, but radians. Let's relate this to things we already know. Like degrees. We know degrees, and we know that when a point on a circle rotates, let's say it starts here, goes all the way around in one rotation, it comes back here, it has performed one revolution. We start at A and we come back to A. So the questions here are, what distance S was covered, and how many degrees were swept out by this full rotation? The point moved around the entire circumference. So I'm pretty sure by this point you guys all know the circumference of a circle. 2 pi r, right? So it traveled a distance, a linear distance of 2 pi r, and we swept through 360 degrees of angle. So we're going to use our angular displacement definition. Theta is equal to 360 degrees, or it's equivalent to it, right? Because we are defining theta as a radian. It equals S over R. S is 2 pi r divided by r, and we get 2 pi radians. So we have 360 degrees using our old conventional measurement equals 2 pi radians. And recall, right here we had no units, but since we're talking about rotational motion, we came up with this radian thing. So we have 360 degrees equals 2 pi radians. We do a little bit of dividing. We divide 360 by 2 pi, and we come up with the fact that 1 radian is 57.3 degrees. So when this arc length here is equal to r, we will have 57.3 degrees right there. To summarize before we move on to our problems, when an object makes one complete revolution around a circle, it sweeps out an angle of either 360 degrees or 2 pi radians. When you do the division, you find out that 1 radian is 57.3 degrees. We abbreviate the radian as rad, R-A-D. You have to be careful about the settings on your calculators. Up till now, you've probably just had your angles set for degrees, or you didn't even know you had that capability on your calculator. You now need to set your calculator for radians for rotational motion problems. Please ask a classmate or your teacher for help on this, or look it up on the web.